Welcome back to RandomMathsInc and another episode of 12 classes. Today is the 10th episode, I believe, of 12 classes, and I'm going to be talking about probably my favorite physics class that I have taken so far. Probably will ever taken as well, looking from the courses I do have left. And the class that I'm going to be talking about today is a class called Statistical Mechanics. So let's get right into it. So statistical mechanics, what is it? What is it all about? Well, statistical mechanics is a field that's really related to thermal physics. So I think I'm going to talk about that one first. So thermal physics, right, is a field that sort of deals with heat and energy and how that affects different systems and so on. So the simplest system that you might see in thermal physics is a system of a piston. So you might have, for example, just a cylinder, and you might have a piston connected to it, right? Now, this in here, you'll have some gas lying in there, right? So the gas, many gas particles, something like that. And you can do different things on this gas. So two key things you can do on it is you can compress it and expand it using this piston here. You can move it back and forth and change the volume of the gas. If you sort of push it in, then you sort of are doing work upon the gas because you're sort of compressing the gas, something like that. So you can do work upon the gas here, but you can also, heat up the gas or apply heat, maybe like light a torch under it, and then you'll give it some heat energy. And so you sort of learn about the interactions between, like, if you have a system, you do some work on it, or you apply heat on it, like how does it affect the system of gas that you have inside. So you might have heard of things like the laws of thermodynamics. The first law of thermodynamics, basically like that the internal energy of the system would just be related to the heat and the work that you do in the system. The D is just to represent change. You might have seen it written in this form or something like that. It's very similar. Some people write a plus instead of a minus, conventions. But basically you learn about like how does externally changing something about, or externally affecting the system changes how it behaves, those sort of things. You might learn about gases, and gases of course have different properties. You can, for example, measure the pressure or maybe the temperature, the volume of the gas, those different things, and you can sort of see how they will relate to each other. If you have an ideal gas, which is a gas that's whose particles are infinitesimally small, like really small particles, and also the gases where each particles don't interact with each other, things like that. You might have, for example, the ideal gas equation, PV equals nRT. If you're a chemist or if you're a physicist, you'll write it as PV equals big N KT, where the small n represents how many moles of like gas particles, and the big N is just the number of gas particles, those sort of things. So that's the ideal gas equation. Those sort of things are the things that you sort of maybe will talk about in thermal physics, and I learned about how affecting the gas on a big scale changes like the properties of the gas. But the problem is, often some of these things are maybe a bit more empirical, right? So for example, like the way that they discovered some laws about the gas was that they actually took a physical gas, like I don't know what gas, maybe like helium or something, and they actually heated up the helium, changing its temperature, but then keeping in the same container, keeping the V constant, and then seeing how the pressure varies, those sorts of things. And then they managed to, for example, take out a graph that looks like that. Maybe like, say, if I change temperature, P changes in this way, those sorts of things, actually making physical measurements. Now the question is, sure, this works perfectly well, but maybe we want a deeper explanation of why it works. This only proves that the laws might work, but we want a deeper explanation of why, like the gas actually behaves in that certain way. And in order to do so, we can't really just talk about the gas, well, as a system as a whole anymore. We have to look a bit deeper inside the gas and then consider the actual particles that are inside the gas. And that is where statistical mechanics comes in. Well, statistical mechanics is made up of two very scary words, the word statistics and mechanics. So let's talk about those two individually, right? So first, mechanics. What is mechanics? Well, we've talked about two different mechanics classes already so far in this series. We talked about classical mechanics and we talked about quantum mechanics. And both of those classes, shares a similar idea. Is that they talk about motions, they talk about properties and how different object moves, right? So mechanics talks about motions and movement, right? But of course, in classical mechanics and in quantum mechanics, you look at it from a slightly different view, right? In classical mechanics, you're more concerned with one particle and maybe how it moves, maybe where it is, or its displacements, things like that. You sort of have Newton's laws, which can describe the individual gas particles' motions, and so on. In quantum mechanics, it's slightly different because you don't have a definite idea of velocity, or you don't have a definite idea of position because everything is probabilistic, and so you have wave functions. But in a way, these wave functions still describes the motions and movements or positions of the objects or of the particles that you have. So mechanics sort of just talks about the motions of different things and things like that, maybe velocities of particles and so on. What does statistics then have to do with the mechanics? Well, go back to this example that I had of the gas particles in a box, right? So if I want to do any meaningful physics with this system of particles, then what I'd have to do is I'd have to take this box, right? And then I have to, for example, consider all the particles within that box, right? So for example, if I want to measure, like the pressure of the gas, maybe I have to consider the motions of each of the individual particles and how they would move. So maybe I would say, how does that particle move? What its velocity would be, right? Or how does that particle move? What its velocity would be? What happens if two particles then eventually comes in and collides with each other? How would they bounce off each other? And then from there, maybe you can use the individual motions of each of the particles in order to calculate the pressure, because the pressure is obviously just a particle hitting a wall, right? And then bouncing off. And then that bounce will sort of exert a force on the container wall and things like that. So if you want to know, like, for example, the pressure in really precise details, you'd have to be able to track each of the individual particles and see the motions of each of the individual particles. And that would sort of fall under mechanics because you're talking about the motions of different particles. The problem with that is that often this is not really practical because of just how many particles you have in a real gas. Of course, sure, here I only drawn like 9 particles, I think. But in real life, you don't just have 9 particles, you have many, many more particles. So if you have a mole of gas, which I can't remember how big it is, but like pretty big, then the number of particles that you have will be on the scale of 10 to the 23, which is a lot of particles, right? Even if you have a glass, if you have like a small glass like this, and you have like and you close it off and you consider all the gas particles inside, even though it looks like empty space, that's still many, many different particles. N could still be on the power of 10 to the maybe like 18 or 19 or whatever, because I don't really know. I don't really scale things that well. But the point is N will still be big, or the number of particles you have inside will still be big. And at that point, it's impossible to do any meaningful physics with it because of how many particles we have. It's not like classical mechanics where you're usually only considering one particle, or maybe at most one rigid body, something like that. So now you can't do mechanics the way that you do for classical mechanics. You can't just use Newton's laws, apply it to every single particle, and then find the pressure or find the velocity of the particles and things like that. And so you have to do something else that is a little bit more clever. So instead of talking about motions of each individual particles, you sort of talk about the collective motion of the particles. What do I mean by this? So rather than talking about what will the velocity of this particle be, you can talk about, for example, if you have this many particles, how many of those particles will move with this velocity, right? So how many out of these particles will move with a velocity of maybe, for example, 10 to the 4 meters per second, something like that, right? So instead of talking about each individual particle, you're talking about the whole particle, and you're using concepts of, like, for example, probability. So you maybe have something like a probability distribution where you can sort of maybe say, right, so I have this amount of particle which will move between this velocity and this velocity, something like that. And so you don't know the velocity of each individual particles, but you sort of know like the proportion of particles that might be moving at a certain velocity. And that is a lot more useful information and something that's actually a lot easier to calculate. So in statistical mechanics, you're talking about the motions and you're considering the state of the particle as a whole, as a group. And then from there, for example, being able to know like roughly the distribution of velocity of the particles, or maybe of some other states, of some other things of the particle, how does that, what we call microstate, or like how, not exactly microstate, but the properties, the smaller microscopic properties of the particles, how does that relate back to the big properties of the gas that we can observe? So for example, how does the velocity of the gas moving in a container, how does that maybe affect, for example, the pressure of the particle or the temperature of the particle, or how does that affect each other the other way around? So that's the idea of statistical mechanics, considering things on the smaller scale and then making models about how things might behave on the smaller scale, and then seeing where you can what that means in the more macroscopic scale, linking back to, like, for example, the particles back up here. Now, I realize that the video is already about 10 minutes, and I've only just explained what statistical mechanics is, and if you want to close away, like, that's actually perfectly fine, because at this point you've seen like the basics of statistical mechanics. But maybe I can give you a bit more example of things that you might find in statistical mechanics, which might help you, be a bit more interested in what the whole field is actually talking about. So as an example, maybe you can consider something very simple, a very simple case. This is something that I've actually talked about on this channel before, which I will just mention again because I think it's a very interesting concept. So as an example, suppose we have a container like that, and maybe you have like a barrier or a membrane blocking off between the two sides. So suppose I have I have some gas particles lying on one side of the container, right? What would happen to the gas particles if I leave it over time? Well, if this is, for example, if I have like a bunch of gas here, for example, one example you can think of this is, for example, if you have two rooms or two sections of the room, and someone comes into this side of the room and farts, then what happens, right? Well, the farts will start off at this side of the room, but eventually over time it will spread across the whole room. So same with gas particles. If you have gas particles on one side of the room, eventually over time, if you wait long enough, then eventually all the gas particles will sort of distribute itself out equally between the two sides, right? Or about equally between the two sides. The gas particles won't stay on one side of the room, so for something like that, right? Why is this the case? Well, one way you can think of it is you can think about, the two states individually, like as a more microscopic scale. So one thing we can do is, for example, I will draw the particles, but instead of having the particles looking the same like this, just for this example, let's suppose the particles all have different colors. All right. So let me actually get all my pens out. So suppose we have many different particles, all of different colors. Some of them you might not even be able to see because of how small it is. So suppose we have many different particles, all different sizes. I only have 6 colors, so I think 6 is probably enough. I don't even know if you can see all 6 of them. But, so I have 6 particles, something like that. I realize you can't even see like the yellow one and light green one, right? So, as you can see, we have 6 particles on one side and no particles on the other, right? If, for example, if I just have 6 particles and I just throw them out into the room, what is the probability that all 6 of them will just clump together on one side of the room? It's pretty small, right? If you have 2 rooms, like of equal sizes, if I take a blue particle, equal probability of being on either side of the room, then there'll be 1/2 probability being on that side. But the same for any particles, right? So the probability would be something like 1 to the power of 2 over 6, something like that, right? You can't even see that, right? 1 over 2 to the power of 6, something like that. But if instead of this, you have the particles equally distributed between the two sides, right? Then the probability of that happening is actually a lot higher, right? Because this is not the only way you can have 3 particles distributed evenly between the two sides. There are other ways that you can do so as well, right? For example, maybe you can have like you can have like this red particle in here, the blue particle in here instead. That would be another way you can do so, right? And so it's the same idea as up there, where some arrangements of particles are more likely than another. So this state is very unlikely to just happen and occur in nature, but this state is a lot more likely because the particle has got a lot more ways to spread it out evenly compared to having just one way to just clump everything on one side, right? This you have this one you only have one way of arranging. This one, in this case, you might have 6 choose 3. I'm not going to prove why that is the case, but that is a bigger number than 1. That is bigger than 1, right? So there's more ways that you can arrange particles distributed evenly. And so it just turns out that because these sort of states are more likely, it will just happen more often, right? And that's sort of the idea behind things like, I think it was like the second law of thermodynamics, where things tend to spread itself out, right? And the things tend to spread itself out because that is just what is more likely than the other, right? You can also link in the concepts of entropy. Like states like this tends to have a lot less randomness, because if you know that it's in this state where all the particles is on one side, there's nothing like really random about that. It's sort of like it's pretty fixed, right? Because one way you can think about it is if I tell you that all the particles are on one side, well, there's only one way you can do that. But if I say all the particles are spread out on to the two sides, there's a lot more arrangements that you can do that. And so you're a lot less certain about what method, like what actual arrangement it might be in. So this one has got lower entropy. This one has got a high entropy. Entropy is a concept of randomness, and but in a more statistical mechanics sort of way, it relates to how many ways you can, arrange itself to give a certain property. So it's sort of like what we call, the actual word is like the multiplicity, right? And the multiplicity of this is higher because there are more ways you can arrange the atoms to get this state compared to this, something like that. That's the idea of like second law of thermodynamics. Now there are also other concepts that I could have talked about. So for example, if you've seen like what I did earlier, not that. You can see what I did earlier here, where I sort of described like the velocity of the particle in terms of, or the speed of the particle in terms of, for example, the external state, maybe in terms of its temperature or something like that. That fits under something called like maybe the Boltzmann distribution, which I think is a little bit too complicated to explain this video, so skip that sort of thing. But statistical mechanics is actually a very useful field as well. Like you can like use it to apply to examples which maybe are even closer to real life. So another example that I can think of off the top of my head is the idea of something called heat capacity. So what exactly is heat capacity? Well, a simple way you can explain this is to consider an example. So suppose I have just a block of metal or a gas or whatever, and suppose I want to increase the temperature of this block, right? Well, what do I have to do to increase the temperature of the block? What I have to do is I have to heat it up, right? Give it some heat energy, right? But what is this actually really doing, right? When I heat the block up, what I'm actually doing is I'm taking the energy from the surrounding and I'm giving it to the block. So the block will have a higher internal energy. I'm not sure if this is the actual term that I used, but that's the idea. So you give it some energy, you heat up the block gets some energy, and this energy then sort of affects how the temperature of the block will be, right? So if you heat the block up, the block gets more internal energy, and roughly the block gets hotter, meaning that its temperature is increased. And how quickly this temperature increases with like the heat going in is sort of the heat capacity. Heat capacity sort of tells you about how quickly the internal energy of the block here, or of any material, changes with respect to the temperature. So I can write the equation of heat capacity. It basically is dE by dt. This is called the partial derivative. It sort of tells you the rate of change. So if you just read this equation of the heat capacity is basically just the rate of change of internal energy with respect to temperature, right? Which, in other words, is basically saying that it talks about how quickly the internal energy changes when you increase the temperature, right? So a high heat capacity means that in order to increase the temperature by maybe, for example, 1 degree Celsius or 1 degree Kelvin, you need a pretty high increase in internal energy, meaning that you need more heat. So some materials with high heat capacity, you need to give it more heat in order to raise its temperature up by a little bit. So a lower heat capacity means that you just heat it up a little bit, temperature will just go through the roof, that sort of thing. And the reason that is the case is because a high heat capacity means that the internal energy increases a lot slower as temperature increases. Meaning that if you try to the high heat capacity means that the energy increases a lot quicker than temperature. Meaning that if you increase the temperature by a little bit, its internal energy increases by a lot. But basically, heat capacity is a property of a material. So, for example, like things like water will have a heat capacity, and heat capacity of water turns out to be higher than a lot of the metal. And the reason I know that because I have a table of it like right in front of me. But you can, for example, use very basic models in order to explain, heat capacities of different systems. So, for example, ideal gases, you can also find the heat capacity of an ideal gas. So it turns out that the energy of an ideal gas is equal to 3/2 nkt. That is a fact that you can prove using statistical mechanics. Why is it 3/2 nkt? Why is that the energy? The energy mostly comes from the kinetic energy of the particle moving inside, which I won't show. And so you can show that heat capacity of ideal gases would just be equal to 3/2 nk, which means that heat capacity just depends on the number of particles inside the gas, something like that. That's a more basic example. But then you can also consider, for example, heat capacities of maybe solids, right? And I'm not going to show you the maths again, but here's one way you can think about, why heat capacity of solids might exist, where it might come from. So in solids, you have atoms, and atoms maybe will have different energy levels. So like in quantum mechanics, right, there's different energy levels that an atom can be in. How do I represent energy levels? So there will be energy levels. There'll be some levels which has got lower energy. There'll be some levels which has got higher energy. Maybe there's more than one level, and maybe the levels are unequal between like the different states and something like that, right? So in these different levels, there can be atoms or there can be electrons occupying these different levels. In reality, in statistical mechanics, it's not really electrons, but I think I'll just describe it as electrons. It's really just more like phonons or something like that. But some particles, some electrons, there is a chance that it might occupy some of the states, right? It might occupy like some of these states, but you're not really sure. But what you can write out is that the probability of a particle occupying any certain energy state will be proportional, like how much probability of it occupying any certain state will depend on the energy level that it is in, so how high up this scale it is in, and also the temperature of the system. So if the temperature is higher, maybe the particles here might want to also occupy some of the higher states, something like that. If the temperature is 0, then it tries to occupy the lowest state possible, so you won't see any particles in these higher states. So the probability depends on the energy level it's in and also the temperature, right? So at any point in time like this, you can find the internal energy of the system. So you can just count, like, is there an atom in this? Is there something in this energy level? If yes, then that contributes to the total energy. So the total energy will just be the sum of all E which has a particle, right, in it, something like that. Now, as you increase the temperature, well, because the probability depends on E and T, when you increase the temperature, sometimes the particle might want to move and jump to a higher state, something like that. Maybe it wants to move to a different state. Sometimes, maybe if you have an energy state all the way down here, right, and something like that, maybe it cannot jump to a higher level because the higher level is already full and it doesn't have enough energy to make a really big leap, something like that. So maybe it stays there, maybe there's other particles moving, something like that. And as you can see, when temperature increases and the particles sort of move between different states, the total energy sort of changes as well. And so in a way, you can work out how does this energy sort of changes as temperature changes, and then from there, you can find the heat capacity of a solid. So that is like basic heat capacity of this thing, right? But basically, yeah. So that is one way you can sort of use you can use statistical mechanics in a more physical system. You do a lot of these sort of things in solid state physics as well, where you're talking about solids. Solids are made of atoms, so you have to discuss atoms. But basically, statistical mechanics is just that. And it's a very interesting field of physics. It's probably my favorite because of how you take something that you might have seen in the big scale, something you can observe, and then you try and describe it using something really small, something like that. And it's great. It's a great field of physics. I really enjoyed it. It's probably my favorite physics class because of that, because of how like it considers things on such a small scale, and somehow it works, and it works in the real life as well. Those sorts of things. But anyways, I think that's enough for this video on statistical mechanics. Hope you had a great. Maybe hope you have a better idea of what this is now. So anyways, thank you very much for watching this video on 12 classes, and I'll see you guys tomorrow for the 11th episode of 12 classes, where I talk to you guys about a computer science class, or maybe a maths class that I've taken that I've also really enjoyed.